In this short segment, we're going to talk about wind and wind-generated waves. We'll spend some more time in a later unit speaking more specifically about water waves, surface gravity waves. This is focused on how just the linkage between wind and wave generation. The generation of waves by wind, there's a few actually competing theories, but the basic idea is that at very low levels of wind, capillary waves are made in the water, giving roughness to the water. And then these waves can grow via a feedback mechanism, whereby as the wind blows over the surface, it produces suction on the backside of the wave, which intends to enhance the growth of the wave. So the primary source of energy for these surface waves is wind. So we're talking about wind-driven waves. Exactly how the waves built from the wind is still a bit poorly understood, but they still can be modeled quite accurately. Wave energy can travel very far. So a storm in the middle of the Pacific can generate waves that reach the coast of California with very little attenuation. The primary attenuation mechanisms are white capping and braking. When the waves start to feel the bottom, the friction will slow the wave, and as well as a very small amount of internal friction. Waves are typically modeled using what are called phased average or spectral models. I'll show you an example of a wave model at the end of this. But rather than resolving each wave and the interaction of each wave, which would be computationally very difficult and can only be done at this point up to scales of roughly hundreds of meters by hundreds of meters, what's done is these wave models will solve for the spectrum and how the spectrum evolves. And by spectrum, I mean how the wave energy is distributed among different length scales, frequencies, and directions. That spectra will transform based under wind stress, under interactions, wave-wave interactions within the spectra, when it reaches shore, and when it interacts other forms of forcing. Typical wave models, SWAN, S-wave, WaveWatch, they're all quite similar in the sense that the equations they're solving are a very similar set. So when you see a forecast, it's based on the idea of a spectral evolution. Wave statistics are quite complex, and so we can apply a length or a frequency and a height to a given set of waves. When you actually look out the real wave field, like around the sailboat, you can pick out some dominant parts of the spectra with your eye, but you can see that it's made up of waves of all different sizes, and you make a recording at a single site of waves, and that's exactly what you see. You see all different kinds of wavelengths and wave sizes passing by the site. The bottom here is a wave buoy, bottom right, with a few anemometers on it and some other instruments. Typically what would be used by NOAA, deployed a fixed site to measure sea surface temperature, and airspeed, as well as wave conditions. These buoys measure waves essentially by measuring acceleration and then integrating that twice to get to the actual position of the buoy. So looking at a complex field like this isn't very helpful to describe mariners. What is the sea state like at this moment? So we boil it down to some statistics, including significant wave height, which for typical distribution of wave represents statistically the highest third of all waves. Peak period is the period of the waves containing the most energy. And a mean wave direction, so that's the mean of all waves in a time series. You can boil a sea state like this around the sailboat down to these three forms, and it's quite informative for people who are either looking at what's the wave forcing on sediment or mariners concerned about the sea state. Here's a buoy. I just pulled up some statistics, so you can go to NDBC, the National Data Buoy Center, which through NOAA, which has links to a lot of the buoys, offshore buoys, which have real-time and historical data available. This Scripps buoy, at some instant, probably not this instant here, has significant wave height, 3.3 feet, 6 seconds, It gives you wave direction of west-southwest, and as well as the water temperature. So what controls the wave state? There's three critical variables: wind stress, time, and fetch. Stratification and the temperature gradients in the air can have a small effect too, but the wind stress, time, and fetch. Greater the wind stress, the greater the waves. The longer the duration that the wind is blowing, the greater the waves. And the longer the fetch, that's the distance over which the wind blows, the distance over which the waves can build. So that's a length scale, the greater the wave state. Now the waves don't grow to infinity. If we blow a 20 meter per second wave across some stretch of water for an infinite amount of time, the waves will reach some kind of steady state. At some point their dissipation mechanisms will be in stride with their formation mechanisms, and they will taper off. Now whether or not that happens depends on a few factors: whether you reach the steady state, has the wind blown long enough, and do you have enough distance over which to build the waves. For example, you can't build a 10-meter wave in your bathtub. So we look at this as a typical fetch wave height relationship. Down here it says something about the wave characteristics. T is the wave period. That is the time between successive wave crests from the point of view of a fixed observer. So if you're standing on a dock and it takes 5 seconds between waves, you'd have 5, or 15 seconds, you'd have 15 seconds. Surfers often look at these numbers because it's a good gauge of the size of the wave period. These three different curves represent three different wind speeds: 10 meters per second, or 20 knots, 15 meters per second, or 30 knots, 20 meters per second, around 40 knots. And you can see that if you have 10 meter per second wind and it blows forever over an infinite distance, that you can reach around 2 meter significant wave height. And with 15 meters per second, you can reach around 6 meter significant wave height. But you see these other curves, the fetch being the short dash and the duration being the long dash. If either of these is a constraint, then you do not reach the full asymptotic wave height. For example, if the wind's blowing 15 meters per second, but it's only been blowing for 10 hours, it hasn't had enough time to build to the full height, which takes roughly 20 or so hours. In the same sense, do you have enough fetch to even build the wind to the full height if you had an infinite amount of time? For example, if you only have 100 kilometers of water, even with an infinite amount of time, you cannot build to this asymptotic wave state. So this has some influence. So this gives you the fetch and the wind duration constraints on the ability for the winds to build to their asymptotic heights. This is again just a sketch. It isn't perfect, doesn't take into account wave current interactions, shoaling, and other complexities. Another scale that's commonly used by mariners is the Beaufort Scale. These are not fixed numbers, these are sort of guidance numbers here. Essentially, good mariners can look out, they can look at the sea state, for example, very calm, almost glassy, just light ripples on the surface, to frothing, foaming spray, and they can determine the seaman's term: calm, light air, light breeze, gentle breeze. And here you see sort of guidance for typical miles per hour. So sea breezes in our area are considered moderate, or more likely a fresh breeze. And these are the same, these are what you would observe on land. There are also images on the web to see what you observe from a ship. This is the Beaufort Scale. Let me see if I can bring up a website. This website is NOAA's Wave Watch model. This is a spectral or phased average wave model which makes predictions of the wave, the evolving wave spectrum. So the directional and frequency spectrum of the wave field, or the distribution of waves in terms of frequency and direction, is a function of space and time. You can see it here. It may be difficult to see in the video, but essentially the wave directions are the red arrows. The wave height is the color, such that yellow is about 8 meters. That's a large wave. Typical blue is around 2 or 3 meters, and dark blue is about 1 meter wave height. And red is the wave directions. That's the direction of the dominant energy wave. And then there are little black arrows you may not be able to see, which are wind directions, which have the barbs on them, which indicate their strength. You can see how the wave energy evolves. We have these very strong westerlies just constantly blowing around the Antarctic, and you can see the waves that they build. And these waves are almost always there once you get down in the roaring Antarctic region. Up here, you'll see over this evolution. This is a forecast over the course of several days, that there's a storm here which evolves and then progresses away from the North American mainland. And associated with that storm, which has a cyclonic or counterclockwise spin, is a fairly large patch of wave. NOAA also has regional models. Let me see if I can find one. For example, Alaskan waters. So this is a more local domain, higher resolution model for Alaskan waters, and you can see again the evolution of the significant wave height in color and contoured, the wave direction in red arrows in association with the black arrows where the barbs of the tail that are the wind vectors. So this kind of data is available all over the web. There's various agencies that run these kind of wave models. There are also wave models that surfers use where they pay for companies to run high resolution wave models and have people interpret the results for them in the sense of a forecast.